fluid mechanics and fluid machines. Today we will discuss about ideal fluid and real fluid. Ideal fluid assumptions incompressible and non-viscous. Bulk modulus is infinite. Whereas real fluid properties of real fluid it possesses viscosity, finite compressibility, and it has surface tension. Here, ideal fluid is imaginary. That is not exist in nature. No surface tensions for ideal fluid. Purely imaginary do not exist in nature for ideal fluids. Fluid properties, density and specific weight. Specific weight or weight density defined as weight per unit volume, that is mg by v, which is equal to rho g. Here rho mass density, g acceleration due to gravity, specific weight of water 9810 Newton per meter cube. Specific volume and gravity. Specific volume defined as the inverse of mass density. This is the reciprocal of density. Specific gravity or relative density equal to density of fluid by density of standard fluid. Specific gravity of pure water is 1 at 4 degrees Celsius. For mercury, it is 13.6. Specific gravity varies with temperature, hence, it must be reference to a standard temperature 4 degrees Celsius or 27 degrees Celsius. Newton's law of viscosity. The governing relation for shear stress tau mu du by dy mu d theta by dt, where tau shear stress, where mu dynamic viscosity coefficient. Du by dy represents the velocity gradient. D theta by dt represents the rate of angular deformation or rate of shear strain. For a Newtonian fluid, the coefficient of viscosity remains completely constant. Viscosity versus kinematic viscosity. Viscosity is the internal property by virtue of which a fluid offers resistance to fluid flow layers. Dynamic viscosity mu. SI unit Pascal second or Newton second per meter square. CGS unit poise dyne second per centimeter square. Here 1 poise is equal to 0.1 Newton second per meter square. Kinematic viscosity mu. Dynamic viscosity mu by mass density rho. SI unit is meter square per second. CGS unit is centimeter square per or stroke. Conversion 1 stroke is equal to 10 to the minus 4 meter square per second. Viscosity of liquid decreases with an increase in temperature, whereas gas increases with temperature. Liquids in increasing order of viscosity, gasoline, then water, then crude oil, then castor oil. Viscosity of water at 20 degrees Celsius is approximately 1 centipoise. Viscosity is physically driven by molecular cohesion forces and molecular momentum transfer. Classification and types of fluids, fluid typology matrix. Newtonian fluids follows linear laws. Non-Newtonian fluids, non-linear relationships. Time independent, dilatant, Bingham plastics, pseudoplastics, time-dependent, thixotropic, and rheopectic. The general rheological relations between shear stress and velocity gradient is tau is equal to A du by dy to the n plus b. A b are represent structural fluid constant mapping the flow environment. Rheological behavior breakdowns. Fluid type dilatant. N is greater than 1, b is equal to 0. Water quicksands. Bingham plastics. Example gel, drilling mud. Pseudoplastics, paint, paper pulp. Thixotropic, ink, enamels. Rheopectics, gypsum mold, clay slurry. Bingham plastics always demand a specific threshold yield stress before initiating any continuous strain profile. Compressibility and bulk modulus. Compressibility beta, reciprocal of the bulk modulus of elasticity minus dV by VdP, dou rho by rho dou P, where K bulk modulus, rho density, and V volume complement. Isothermal bulk modulus KT, adiabatic bulk modulus Ka. Here KT is equal to P final is equal to rho RT, whereas K is gamma P final, gamma is Cp by Cp ratio of specific heat value under constant pressure and constant volume conditions. Surface tension and internal pressures. Surface tension occurs at liquid gas interface due to uncompensated cohesive forces. It acts when fluid is at rest and decreases with temperature. Geometry type. Gauge pressure equation formula. Liquid droplets, solid like spheres, P is equal to 4 sigma by D. Soap bubbles, thin hollow shell, P is equal to 8 sigma by D. Liquid jet, cylindrical columns, P is equal to 2 sigma by D. Surface tension facts. Surface phenomenon evaluated as force per unit length. Water air interface at 20 degrees Celsius has sigma 0.0736 Newton per meter. At the critical point, the liquid vapor boundary dissolves, leading to sigma tends to 0. Capillary action, rise and fall. The absolute height displacement within a narrow tube is modeled using mechanical forces balances. H is equal to 4 sigma cos theta by rho GD, where H vertical capillaries rise by depression, sigma surface tension coefficient D is equal to diameter of the narrow tube and theta contact angles. Theta is equal to 0 degree for clean water glass and 120 degree for mercury glass. When the fluid surface supports another lighter liquid layer of density rho b, H is equal to 4 sigma cos theta divided by rho minus rho b dt. Capillary action require both adhesion and cohesion to occur spontaneously. To produce a distinct measurable capillary action, the internal tube diameter must strictly remain less than 3 cm.